Hey guys, today this is the Academic Chemistry, Chapter 3, Section 2 notes, the International System of Units. Today we're going to be learning about how to take measurements. So what kind of things do we use to describe our measurements? If I said to you, oh yeah, that thing over there is 3, you're going to be like, 3 what? So whenever we take measurements, we have to explain what we mean with those numbers. I kind of have a joke over here. The teacher tells us about grams, milligrams, and kilograms, and the kids say, what about Instagram? We will not be using Instagram in class. Okay, so in America, we use what's called the English system of units. Sometimes it's called the imperial system of units. And it's all these things. So you've measured things in inches or feet, yards. You've used a cup, a quart, a gallon. There's all these different things. And if you grew up in America, that seems totally normal for you to like use the Fahrenheit, for example. But the rest of the world doesn't use that. Now, there are some exceptions, like England actually does use miles sometimes. So if you watch a TV show and they have an English accent, they'll suddenly say miles, and you're like, what? That's crazy. But besides that, everybody uses something else. So the reason is there's no easy way to convert between units measuring the same type of data. So like it's not easy to go from inches to feet, or inches to even yards would be even harder. So I want you to think about it. Do you know how many feet are in a mile? Because it's 5,280 feet in 1 mile. That's not an easy conversion. If I needed to just switch between feet and miles, you'd probably give me this face. I don't think so. It's not an easy conversion. Now in science, we're going to use the International System of Units. And you might also hear me call that the metric system. Now technically it's not the metric system because there's a few minute differences, but for all we're going to be doing, I'm going to call it the metric system. Um, so the reason why this is nice is it's based on the base 10, meaning things are multiplied or divided by 10 to convert between different types of measurements. And they use prefixes. Pre means before. So when you talk about something before the word, it's either being multiplied or divided by 10. And if you remember from elementary school, whenever you divide something by 10, you take the decimal and you just move it that many spots to the right, right? Whenever you multiply by 10, you keep all the same digits, you just move that decimal over to the right to make it bigger. So it's nice and easy because we're not going to change our numbers, their actual digits. We're just changing how many or how small. And we'll go over that a little bit later, and then especially more in Chapter 3, Section 3. We're going to be going through conversions. So one thing you have to remember is SI measurements provide quantitative data about an object, and that's information with numbers. So if I had this tennis ball and I wanted to take some quantitative, quant means numbers. So like quantity is how many. If I'm taking quantitative data, I might say the ball is 58 grams. I might say it's 131 cubic centimeters or 131 milliliters. But one thing I wouldn't say is yellow. So today's whole lesson is all focused on how to take number measurements of something, quantitative. Versus if I was talking about this being yellow, that would be a qualitative, describing the quality of something. So the first one is length. Length measures the distance between boom, boom, 2 points. That is length. Now, back in the day, length used to be described as the length that a king would step. And however big that is, that was their stride. But that would change over time, right? Because you might have a tall king or a short king, or maybe he was feeling tired one day, so they measured something smaller. So it wasn't very specific. Now we use the meter, and the meter is describing length. You've seen meter sticks probably in the classroom. Technically, the meter is defined by the length that light travels in 1,299,792,458th of a second. So if I divided 1 second, 1 Mississippi, into this almost 300 million pieces, however far light would travel in that little bit is a meter. So think about a meter stick. That's how far light travels in 300 millionths of a second, which is kind of crazy how fast light is, but all right. The reason we do this is because scientists around the world can recreate this. So they can make sure their meters are exactly the same as someone in a totally other side of the world. So a scientist at a lab in America can have a meter that is the exact same length as a scientist over in China, and they don't need to check with each other. They can make a vacuum and they can have light travel through. A meter stick is slightly longer than a yard. So a yard is 3 feet. You've probably seen a yardstick before. So this is a little bit longer. It looks like this. And if you look at a meter stick, it's divided into 100 pieces. Those are centimeters. Centi means 100 pieces. So like a century, for example, has 100 years in it. So there are 100 centimeters to add up to a meter stick. And then in between those little bits are actually millimeters, which are even smaller. And those there are 10 millimeters in each centimeter. So remember how I said it's all by tens? That's what makes it nice and easy, and we'll go over that later. Um, Also, we could have kilometers, km, so 1,000 meters is a kilometer. So you've probably noticed this if you are a driver. You'll see the kilometers per hour. So that is the speed that they would use in other parts of the world. They're not going to talk about miles per hour. It makes you feel like you're going really fast when you travel to another country and you are going right here 90 kilometers per hour, but it's really 55 miles. So let's say I was traveling from here to here, and this is 2.4 kilometers. What makes the metric system really nice is 2.4 kilometers, and since I know each kilometer is 1,000 meters, really easily is 2,400 meters. So I didn't have to do much. I knew that a meter is 1,000 times bigger than a kilometer, so I just multiplied by 1,000, which makes my decimal go 1, 2, 3 spots to the right, so that gives me 2,400 meters. It's nice and easy conversion. The next thing we want to talk about is mass. So mass is the amount of matter contained in an object, and we're going to use a scale to find the mass of an object. So we've got electric scales in the lab. You can also use a balance, a triple beam balance. We're going to do a little bit of practice with that, but for the most part, we'll use electronic scales. The kilogram is the base unit to describe mass. Now, what's interesting about this is the only base unit that we include a prefix with. The reason is humans are kind of, we think about ourselves a lot and we would measure ourselves in kilograms. So if you go to another country, they're going to describe when they say how big or small you are, it's how many kilograms you are. So in chemistry, though, in this class, we're generally going to measure things in grams because we're going to use small quantities of substance. I'm not going to ask you to measure a kilogram of, you know, glucose. That would be a lot of glucose. So one thing to note is that it's okay. I like redoing things that I've done already. Love you. Mass is the amount of matter contained in an object. So in the lab, we use a scale to find this. We've used a scale before. You can also use a triple beam balance. We'll do that a little bit, but mostly we're going to use the electronic scales in this class. The kilogram is the base unit to describe mass. What's funky about this is if you notice, it has a prefix. So not just one letter, the kilo is in front of it. This is the only one that the technical base unit is actually a prefix included. The reason is we think about how we measure ourselves often when we think about basic things in chemistry. And if I were to step on a scale, the scale, it would be easier if it read it in kilograms versus grams. If I measured myself in grams, I would have a lot of grams, so kilograms are easier. But in chemistry, we're mostly going to be using grams, and that's because you don't need a lot of something to do a chemical reaction. I don't want you measuring a kilogram of glucose. That would be a lot of glucose. So we're going to be measuring with grams, and that's what the scales in our lab are calibrated to show you. It actually can't even get to a kilogram. That would be too heavy for our scale. One thing to note is mass and weight are not the same thing. So weight is the effect gravity has on mass. And you've got a formula here. So weight is whatever your mass is times gravity. And I know it's kind of funny because this is an M, not meters. That's for mass. times whatever the gravitational pull of wherever you are. So we're on the Earth. So the Earth is really big, so we get pulled to the Earth. So one thing to note is weight has a direction. Like our weight goes down to the ground, but the amount of matter in something doesn't have a direction. It's just how much stuff there is. So mass doesn't change based on location, weight does. So for example, um, this person's weight on Earth might be 560 newtons. Newtons is how we measure weight in science, but you won't get to that. You'll do that in physics. We won't really be talking about newtons. Versus if you're on the moon has a smaller gravitational pull. So notice this same person, same size person on the moon is now 90 newtons. But the whole time this person was 56 kilograms. And it's just because the moon is smaller, so there's a smaller gravity, so the weight is smaller, but the mass is always, always, always the same. Unless you like chop something in half, then obviously the piece you're left with is smaller. But if you don't change the size of an object, then its mass is always the same. So what is a gram? Well, 1 gram is about the mass of a paperclip. So think about how much stuff is in a paperclip, how that feels in your hand, and that's about a gram. A kilogram is 1,000 grams. So you can either think of 1,000 pineapples, or I'm sorry, 1,000 paper clips, or you can think of 1 pineapple. So about the mass of a pineapple is about 1 kilogram. The next thing is volume, and that's how much space something occupies. So liter is the base unit for volume, and you've probably seen a liter of water, right? So hopefully you're drinking at least one of these a day, because that is healthy. So 1,000 milliliters is 1 liter. Milliliters is very common. So a milliliter is small because you need 1,000 of them to get up to a liter. If you ever have had a shot, which you probably have, they've measured this in milliliters. So when they are filling it, they will pull back the plunger until they fill it with the volume or milliliters of that vaccine that you're getting. We use a graduated cylinder to measure volumes. So this is that graduated cylinder. It is skinny, so that way you have a lot of graduations, these little lines. You can tell exactly how much liquid is in there. But the thing is, solids also take up space, and they're measured in meters cubed or centimeters cubed. And you're like, meters? That's what we did in length. And yeah, it's because it's height times width times depth. You've done this in math class before. So if we have this cube, whatever this length is, times this length times this length. So that's what the cube comes from, or to the third power. One thing to note is a milliliter is the same as 1 cubic centimeter. So if I had this box that was 1 centimeter by 1 centimeter by 1 centimeter, I multiply those all together, and that's going to be a 1, because 1 times 1 times 1, all those measurements. And then I have 3 centimeters multiplied together, so that's why it's to the third power. If I could fill this little box with liquid, I would fill it with 1 milliliter, because 1 milliliter and 1 cubic centimeter are the exact same amount of space, like how much space in front of you it takes up, or in a milliliter, how little bit it takes up. But then some things aren't easy to measure with a ruler. Some solids are going to have an irregular shape. So let's say I had this little toy koala thing, and I wanted to know how much space it took up. I can't just length times width times height because it's not a cube. So when an object is placed in a graduated cylinder, it has this really interesting quality. If you put water in the graduated cylinder first, then however big that object is, it's going to displace that exact amount of water. So once it's submerged, the water rises, and that's called water displacement. So I would take this toy koala and I would drop it into this, well, I said water, I mean, I've colored it in here so you can see it. So if you drop the koala in, and initially it was 50.0 milliliters, see where this comes to, and then once the koala is in, it's 60 milliliters, then the difference here, it's because of the actual size of that koala, or whatever the object is that you put in. So now I know that this object is 10.0 milliliters. It's a solid though, so I'm going to re-describe it as 10.0 cubic centimeters, because if you remember, a milliliter and a cubic centimeter are the exact same thing, but it's a solid, so I go with cubic centimeters. Another thing we're going to talk about this unit, and especially in 3.4, we're going to have a whole section dedicated to this, is density. And density just describes how packed atoms are together. So anything that's matter is made of atoms, these teeny, 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 tiny particles that make stuff up. If there are a lot of particles in an area, then that's a high density. If there's few, if there's low density, it's used as mass per volume. So grams per milliliter is a common one you'd see. You might see kilograms per liter, but as long as there's mass, some sort of mass on top and some sort of volume on the bottom. If you look at these pictures over here, this is going to be a low density compared to over here. This would be a high density, and that's because there's less things per area and there's more things per area. Now, if I were to put these two things on a scale, notice they take up the same amount of room. So this over here on the left, the lower density is going to have less mass than this object over here on the right with a greater density because they have the same volume. So even though they might be the same size, they might take up the same amount of space, one might have less mass or show less on a scale versus the other. All right, to finish this up, in the International System of Units, we have these things called prefixes. And pre means in front of. So it literally goes boop in front of the word and it changes the scale by a factor of 10. So here are the prefixes that you want to become familiar with. So for example, if I were talking about a microgram, so say I was trying to describe the mass of a cell, like a little bacteria, so a microgram. Micro is right here, 10 to the negative 6. Micro is kind of funky. It looks like this is a better picture for it. It looks kind of like a P and a U came together to make some brand new symbol. It's mu is the Greek letter. Anyways, when you're drawing it, if you are putting the abbreviation, the prefix goes first, just the letter of the prefix. So this one is micro, that's the prefix, and that's saying how big or small. And the second letter you see, gram, G is your base unit, and that tells you what you're measuring. So this is measuring mass of a really small thing because micro is small. So if there's a positive number on your exponent, so that's these over here, then that means that it is bigger than its base unit. So if you plop that in front of a base unit, so say you have kilograms or gigagrams or exagrams, that is bigger than a gram. All of them are. And it means that you're going to multiply your base unit by 10 that many times. Versus if you have a negative exponent, all of these are all smaller than your base unit, and you'd actually be dividing that base unit into that many pieces, so dividing it by 10 that many times. So here's a number line that I put together, and I have all the prefixes that you really need to know for this class on here. There's going to be some that aren't on here that you saw on the slide before, because a lot of them aren't used very much, so these are the ones that are really used a lot in science. Those are the ones that I care that you know. You'll notice that all the positive ones I put over here in blue, which you might think is kind of weird because generally you put bigger things on the right, but right now they're on the left. I know it's crazy. In chapter 3, section 3, I'm going to explain why that is helpful to kind of have a reverse number line right now. All of the negative exponents are here on the right, and they're all in red. Notice in the center I have the base, so that means no prefix. Let's go over a few things. So a centimeter. So if I were adding this prefix, centi, to meter, centi means 10 to the negative 2, or divided by 10 divided by 10, which is also divided by 100. So that's why a centimeter is 1/100th of a meter. Because if I took a meter and I divided it by 10, then I would have 10 pieces. And if I divided each of those by 10, then I would have 100 pieces. So centi means I took my meter, or whatever, it could be a centigram, I took my base unit and I divided it into 100 pieces. Next, if you look at a gigabyte, so you've probably heard of this when you've been buying phones or computers or something. So what is a gigabyte? So giga is one of these prefixes, and giga is right here. It means 10 to the 9th. And notice that's a positive thing, so it's bigger. So a gigabyte is bigger than a byte of information. You do not want a byte of information. It won't store very much. So what is a gigabyte? Well, it's 10 to the 9th bytes. What's 10 to the 9th? So it's a positive number, so you're multiplying. So it's whatever you have. So if you have 1 GB, it's 1 times 10 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 times 10, otherwise known as 1 GB is 1 times 1,000, I'm sorry, times 1 billion bytes of data storage. So that is a practical use outside of chemistry for the metric system. Yay! All right, so best of luck with your work with the International System of Units or metric system. Make sure you come talk to me if you have any questions, and good luck. Okay, I'll see you in the next video.